Hello, and welcome to our last video of Chapter 7. So Chapter 7 is super short. This video is also going to be kind of short because we're just continuing on from what we did last time. So last time we talked about sampling distributions, and then we focused on sampling distributions of sample proportions. So rather than dealing with proportions today, now we're looking at means. So with means, remember this means that you are going through every combination of like a certain size sample and calculating the mean, the average from that sample, and doing this a bunch of times. And with that bunch of times, you're making a big graph, a big dot plot or whatever, and then out of that graph, what is the center, variability, and shape. So similar to last time, but with means this time. Because the center and the variability changes with means instead of proportions. So when we talk about the center, the mean of the sampling distribution matches the population mean. So whatever the population mean was, then our center for our sampling distribution is going to be the exact same number. For the variability, the new standard deviation is used by finding this formula. So you're going to take the old standard deviation, whatever they give you in the problem, divided by the square root of n. N stands for your sample size. So the interpretation for our standard deviation is that in samples of size n, whatever your sample size is, the sample mean typically varies from the population mean by whatever number you get for the new standard deviation. So basically we're saying every time we get a sample mean, when I take that sample, find the average of it, it's going to be off from the actual population mean by that amount. So, because that's the definition of a standard deviation. The shape is similar to what we had before. The shape of our distribution is going to match the original population. But just like before, we had like a way to kind of make it normal. So with proportions, we did that n times p, n times 1 minus p had to be greater than 10. With means, you can't do n times p or n times 1 minus p because we don't have a p. P stood for the proportions. We don't have proportions when we're dealing with means. So we can't use that rule, but we have this thing called the central limit theorem. So central limit theorem says when your sample size is big, like greater than 30 is how we define big, then the shape of the distribution is going to be approximately normal. So that bell-shaped curve, which is what we want because that's how we calculate our probabilities. So let's do an example. At the Nutty Peanut Company, dry roasted shelled peanuts are placed in jars labeled 16 ounces by a machine. The distribution of weight in the jars is approximately normal, so they're telling us it's approximately normal already, with a mean of 16.1 ounces and a standard deviation of 0.15 ounces. Let x bar be the mean weight of 10 randomly selected jars. Find the probability that the mean weight of 10 randomly selected jars is less than the advertised weight of 16 ounces. Okay, so we already know it's approximately normal, so we can draw our normal curve. And we can find our new mean and standard deviation because now we're dealing with a sample size of 10. Okay, so since they told us the mean of the original was 16.1, we know the mean here is going to be 16.1. And then they told us our standard deviation was 0.15 ounces. So when we calculate our new standard deviation, we're going to do the old standard deviation of 0.15 divided by the square root of n, where n for us was 10. When I do this out in the calculator, I get 0.0474. Now we're finding the probability that the mean weight is less than the advertised weight of 16 ounces. So shading from 16 and then less than that, so to the left. All right, so here's the shaded portion I'm trying to find on the normal curve. So we do our z-scores, use the table to find our percentage. So plugging into my z-score formula, I have my value of 16 minus the mean of 16.1 divided by my new standard deviation of 0.0474. When I do that, I end up with negative 2.11. So now we're using that number to look in our table to find the percentage. And since it's an area to the left, whatever number, whatever percentage I get, that would be my answer. So let me scroll down. Negative 2.11 is right here. So 0.0174 or 1.74%. Okay, another problem we want to be able to do is solving for a minimum sample size. So sometimes we want our new standard deviation to be smaller because that means our data is going to be more consistent with a smaller standard deviation. So in order to make our new standard deviation smaller, what we want to do is use a bigger sample size, because when you have a larger sample size for n, then you end up dividing by a bigger number, which decreases your standard deviation. So I'm going to use the same information from the last example. We want our standard deviation of the sampling distribution to be half the original amount. So originally I had 0.0474 as my original amount. I want it to be half of that. So what sample size would be needed? In order to solve for this, to solve for the sample size, I can set up an equation like this. So if I wanted half of the original amount of the standard deviation of the sampling distribution, I can divide that 0.0474 number by 2 to get 0.0237. So that's the new standard deviation that I want. So I'm going to set that equal to how I calculated the original standard deviation, so the 0.15 divided by the square root of n. I just don't know what I'm using for n this time because that's what we're solving for. We're being asked what sample size would be needed. So we're solving for n. This is where we need some algebra skills. So in order to solve this equation to get n by itself, the easiest way to do this is actually to multiply both sides by the square root of n. That way I don't have fractions anymore because, we don't like fractions that much. So if I multiply both sides by the square root of n, sorry, terrible handwriting because I'm drawing on a computer screen, very difficult, then this side will go away. So now I have 0.0237 times the square root of n equals 0.15. To get the n by itself, now that it's on this side, I can divide both sides by 0.0237. And once I do that, if I want to get rid of a square root, the opposite of a square root is just squaring both sides. So finally, I can just square both sides, and then squaring will get rid of the square root, leaving me with just n equals, and then whatever this number comes out to be. So the 0.15 divided by 0.0237, whatever decimal I get from that, squaring it, I get my answer. So that actually comes out to be like 40.06-ish. But remember, this is a sample size. So in a sample size, we're talking about like how many people. We can't really have 0.06 of a person. So for these problems, we always round up to the next whole number. So even though the decimal is 0.06, it's such a small decimal, we're still rounding up to the next whole number of 41. So 41 is the sample size I need as my final answer. All right, in this last example, we're doing something similar, but this time in this problem, we're actually going to go back to our proportions. So it says the makers of Skittles claim that 20% of Skittles candies are orange. So here we're given percentages, so we're dealing with percents. You select a random sample of 30 Skittles from a large bag. Let p hat equal the proportion of orange Skittles in the sample. The standard deviation was found to be 0.0730. What sample size would be required to reduce the standard deviation to 1/2 this value? So again, we're trying to divide this by 2 to get it to half the amount. So we're going to start off using a similar method. We're going to take half this amount to see what we want to end up with, kind of like what we did before here. But then when we solve for n, we're going to end up using a different formula because we had a different standard deviation formula when we dealt with proportions than we did with means. Okay, so dividing our standard deviation that we wanted by 2, we get 0.0365. So that's what we're setting it equal to for our standard deviation formula for proportions. So remember, this was the p times 1 minus p all over n, square root the whole thing. So that was the standard deviation formula from last section. So again, we're solving for n. The 20% was because they told us 20% of Skittles are orange. So now solving this out, in order to get n by itself now, we have slightly different order of steps that we need to do because we want to get rid of this square root first. So this time we're going to square both sides first. Okay, so on the left side, I have the 0.0365 squared. I'm just going to do that in the calculator later. But on the right side, I actually so we got rid of this square root. But then on top, the 0.20 times the 1 minus 0.20 is really just 0.2 times 0.8. So I just solved that out really quick. I also get 0.16 from that. So that's an easy step to deal with. Because now I still have n on the bottom, which is not great because, again, we don't like fractions. So I'm going to multiply both sides by n again. That way I no longer have fractions. So now that n is no longer on the bottom of a fraction, I can divide both sides by the 0.0365 squared to get n by itself. Okay, so I end up with n on one side by itself equals 0.16 from my before divided by the 0.0365 squared. When I do that in the calculator, I get 120.09. But again, this isn't my final answer because we're talking about a sample size here where I can't have 0.09 of a person. So same thing as before, even though it's a really small decimal, we're always going to round up to the next whole number. So my final answer is going to be 121, is going to be the sample size that I want. And that's it for this chapter. Thanks for watching. Don't forget to like and subscribe. Bye.